Hey guys, Jesse here. I got a little sidetracked today and kind of worked on a little project. So what we've got here is an area of interest in the middle where there was some disturbed soils and some work done in the past. And then I've got a buffer zone around it, which is kind of what I'm going to compare it to. This is an NDVI layer from the middle of July when the crop was nice and green, um, like that. And so we're pretty high resolution here. Like you can see pretty well down to the crop row. Um, what I was going to do is some zonal statistics and see if the mean NDVI within this is equal to the outside. And it's not quite, but I was wondering how much lower could that be and still be representative of the field? Because I mean, you zoom out and there's a fair bit of variability around the field. Um, so it's like, how do we characterize the natural variability in a field? So I used Chat GPT extensively here today, and a couple different models like the 4.0 or the 0.1 preview. And what we did was basically take the distribution of NDVI values and we plot them into like a density graph, like kind of like a histogram, and it shows basically the amount of the distribution of NDVI values within a polygon. So my idea was if we take these two curves or these two functions within and without, we can compare those curves to each other and how similar is the shape of one curve to the next, and to see if not just looking at the mean and the median, which can get kind of on these very dense data sets, you can start to see how little things get masked with the huge number of data. So I thought, what if we just look at the shape of the curve? So those are the curves are called um, cumulative distribution functions. And then the method that we're going to use to compare those two is called earth mover's distance, and it's a measure of how much work it takes to change one curve into the next. So we can do that between these two areas and see how different they are from one another. But what that doesn't tell us is that this difference meaningful or not. So then what I decided to do was just for this one, I just randomly drew some polygons. They're called like Voronoi polygons, just randomly excluding our area of interest. And those are going to be our polygons, and we're going to compare basically polygon 1 to the background, polygon 2 to the background, and take this, plot the curve of their NDVI distributions and compare the curves of each of those to kind of get an average amount of variation to the field is kind of my concept. Anyways, it was starting to be a fair bit of Python work to do all this, so I thought it'd be a cool opportunity to step into Replit, which is just this online IDE, and use AI and just see where I can get to today. So I'm going to walk through. I'll share a link to my GitHub. I'm not going to publish this yet to like a live website, even though it could, and we're going to walk through it that way. So there's a README on the GitHub, and here's my main.py file. And keep in mind that I don't know how to code, and I didn't write any of this. It's all been AI generated, and then we debug and troubleshoot and iterate until we get things that work. So I'm going to click run and walk through how I'm going to use this Streamlit app. We'll do move an issue. I'm going to run this app. Give it a second. Should be working. Sorry, I guess it'd been sitting idle too long. So we're going to run this. And now in my shell, we should just write streamlit run main.py. And now I'll open up this new window, and we should have this live website that we made. So I'm going to grab my raster, which is, I'm using just for this one, slightly lower resolution one, and I'll go back and do this again with the higher resolution one, but I was taking up a little bit too much compute resources on my Replit for iterating. Okay, so we dragged and dropped in the raster file, and then we dragged and dropped in the polygon file. So here is the polygons we're bringing in. I've labeled them. So the polygon roles are AOI. That's what I'm calling the area of interest. It's my main analysis area. That was like the disturbed area. Then just for shorthand, ABB. So it's adjacent background buffer, which is that area right outside the main polygon. And then these natural field variability polygons, what I'm calling them, they're how we are characterizing the rest of the field. So we're selecting our AOI polygon, and from up here, my AOI was polygon number 2, or polygon number 1, I guess, because it starts labeling there. And my background buffer is going to be polygon 0. So here we are. One thing to keep in mind is, so my buffer and area of interest are quite a bit smaller than most of these, except for this natural field variability polygon number 5. So here's our stats. The mean NDVI for our area of interest is lower than anything else. So is the mean. Standard deviation is a little bit on the high end. Let's just have a quick look at these visualizations. So here is my CDF, cumulative distribution functions. We're calling it an NDVI distribution here. So pretty cool how Streamlit basically bakes a lot of this in. You don't have to really do much of it. So here we can see each of the curves. So this dark blue, that's my area of interest. And then this is the background. And then these other ones are the adjacent ones. So we see that area number 3, number 1, and number 2, they all have a higher density of NDVI values in this like 0.75 range. Polygon number 4 is this green one. It is like lower NDVI than the background. Oh, and then our area of interest. But it's actually got more density on the high end, right? Where our AO area of interest, it's got quite a bit in this range, but it's got a fair few lower NDVI values also. And then we look at, there are some of these ones we're not looking at. The light blue is our background area. So it's got these two humps. There's like a local peak, just about 0.7, and another one about 0.78. And then this number 5 is kind of interesting. So here we see a different distribution. So we've got a fair bit of healthy stuff here, but there's a lot of unhealthy stuff as well. I mean, I'm learning how to interpret these. This is like a new concept. I've never really used these density functions before. But let's look at these in a box plot now. So here is, again, this was all generated in this little app here by Streamlit. So this is the area of interest we've got. So we can clearly see the median, which is the center line, is lower than all the other ones. The quadrant 1 and quadrant 3, so this is like 50% of the NDVI values, they're actually all lower as well. So here we can start to see, like, right away, there's a shift in from the background. And as we look at these other ones, especially these 3 that had the high peak curves, like, they're a fairly narrow range. This one here actually has a bunch of outliers above, like on the top end of the scale, up into that 0.9. Anyways, then we see number 5, which is that the oddball one. and it's got a wide range of values here. It's more spread out. At least that's how I'm interpreting it right now. So let's have a look and see what this Earth mover distance analysis looks like. So what I decided to do was basically compare each of these field polygons to the background zone, I called it, and take their Earth mover distance, and we're going to average these out. So we can see in the higher the number here, the more work required to make the curves the same. So in polygons 1 through 4, they're all fairly low, and then polygon 5 is the highest, which if we go back to here, polygons 1 through 4 are these guys. They're relatively similar. And then 5 is this oddball one. Again, we need to dive into this a bit more, but so it gives us an average EMD of this 0.081, which is an average of these. And then what I did was take the Earth mover distance between the area of interest and the background, and it becomes this 0.0103, which is higher. So it means it took more work to make those two curves the same than what we're seeing kind of background in the field. So in this case, I'm saying the area of interest fails to fall within the normal field variability because of the larger EMD. Maybe this is all baloney. If anyone has any understanding of this or would care to like chat about it or care to try some of their own data, I'd be happy to work through it. I think it's an interesting idea. I think there's some validity to it. I think I might have to tweak some things here and there, but overall, I think it's pretty interesting. Let me know what you think.